All right, so today we're diving into something pretty wild.
Yeah.
Using quantum physics to understand how our brains work, how we make decisions, and all that.
Yeah, it's a pretty fascinating area, and we're going to be looking at a paper called Quantum-like Cognition and Decision-Making in the Light of Quantum Measurement Theory.
Oh, catchy title. I love it.
Yeah. Mm-hmm.
So, you might be thinking okay, what does quantum physics, which is subatomic particles and all this weird stuff, have to do with me deciding what to eat for lunch or,
Right.
remembering where I put my keys?
Exactly.
But this paper suggests that to really model some of the weird things our brains do, especially when it comes to memory and conscious thought, we might need to go beyond even the standard ways we think about measurement in quantum physics itself.
Yeah, so for a long time in quantum mechanics and in the early attempts to model cognition using quantum principles, this is often called quantum-like modeling, the focus has been on these things called projective measurements. Okay.
And you can think of a projective measurement as a very direct observation that forces a quantum system into a single definite state.
Okay.
But this paper is arguing that if we really want to capture all the nuances of how our minds work,
Right.
we may need to explore a different kind of quantum measurement called a sharp, repeatable, non-projective measurement, or SRP for short.
SRP, Art, I like it. The more acronyms, the better.
Exactly.
And this is what I love about this field is it's we've got quantum physicists over here. They're doing their thing. They're looking at the fundamental nature of reality. And they've mostly been focused on these projective measurements.
Yeah.
But then over here, we've got these cognitive scientists, psychologists, people trying to understand the human mind, which arguably is one of the most complex things in the universe, right?
Yeah.
And this paper is suggesting that to understand the mind, we might actually need to go to this other area of quantum measurement theory.
That the physicists haven't been focusing on as much.
Yeah, it's we're finding this specialized tool in a workshop that turns out to be perfect for this task.
Yeah, exactly. Yeah, we're expanding the toolkit. So for our listeners who want to, get up to speed on this pretty quickly, what we're going to do is we're going to extract the core insights from this research and show how this very precise language of quantum mathematics could give us new ways to understand how our minds work.
Yeah, the core idea is that the way we measure things, even if it's just in a theoretical sense, really deeply impacts what we can learn and what we can know.
Yeah, I like that. So let's get into the nuts and bolts of this paper's argument.
Yes.
So they're basically defining these types of quantum measurements that they think are most relevant for modeling cognition.
Exactly.
And they point out that, projective measurements, those are the foundation of quantum physics. And they were kind of the go-to in these early cognitive models, but they run into problems when we try to explain combinations of certain cognitive effects.
Yeah.
So for example, think about how the order in which you're asked questions can change your answer.
Absolutely, yeah.
Or how, if someone asks you the same question twice in a row, you're more likely to give the same answer the second time.
Yes. Yeah.
Even if maybe you would have thought about it differently if they hadn't asked you the first time.
Exactly. And what's so interesting here, and this is, I think, an important thing for people to be aware of just in their own thinking, is that the paper argues that these projective measurements, they can't fully account for these combined effects.
Yeah.
So it's not just one or the other, it's how they work together.
Right.
And that's where these SRP measurements...
right, the sharp, repeatable, non-projective.
Exactly. They come into play. And the authors are making a really compelling argument that maybe physics and cognition are exploring different facets of the same underlying theory of quantum measurement.
Oh, that's really interesting. So we're all looking at the same thing, but from different angles.
Exactly.
Okay, so then they make this distinction between what they call observable non-commutativity, which is, a familiar concept in quantum physics.
Yeah.
It's you can't measure position and momentum of a particle at the same time with perfect accuracy. Right.
Yeah.
And then there's this state update non-commutativity, which is about how the state of a system changes after a measurement. And the paper suggests that this second type, this state update non-commutativity, or maybe even a combination of both, could be really crucial for understanding these quantum-like cognitive effects.
Yes. It's the way our mental state evolves as we're processing information might be just as important as the information itself.
Yeah, that makes sense. It's not just what, it's how you got there.
Exactly, yeah.
So I think to really appreciate this paper, we kind of need to go back in time a little bit and look at how this whole field emerged.
Yeah. So there was this thing called the second quantum revolution, which really focused on things like quantum information and computation.
Right.
And that movement really sparked this idea of like, hey, maybe we can use these formalisms of quantum theory to understand stuff outside of traditional physics. And cognition was one of those areas.
Right.
And so naturally, those early efforts, they relied on this well-established framework of projective measurements.
Okay. Yeah, that makes sense.
But as those models tried to grapple with like more and more intricate aspects of human cognition, it became clear that they had some limitations.
Right.
Projective measurements alone just couldn't capture the full spectrum of what we see in human behavior.
Yeah, it's like trying to paint a masterpiece with only one color.
Yeah, exactly.
But you need a wider palette. Right?
Yeah, exactly. And this was a really pivotal moment because it forced researchers to realize that quantum measurement theory offers this much richer toolkit.
Right.
Than just those basic projective measurements.
Okay, so then they make this really important distinction between a measurement and an observable. So can you unpack that a little bit?
Yeah, so in quantum formalism, an observable is usually associated with a self-adjoint operator and something called a projective POVM. But simply put, it's a mathematical way to describe like all the possible outcomes of a measurement and their probabilities and how the system collapses onto one of those outcomes.
Right.
But a measurement in quantum mechanics is actually a more general concept.
Okay.
It's defined by two things: the probability of getting each outcome, and then how the system's state changes after you get that outcome.
Okay.
And these two things are combined in something called a quantum instrument.
Okay, so it's like you can measure the same thing in different ways?
Exactly, yeah.
And that can lead to different changes in the system?
Yes, and the authors are arguing that this difference in the state update process might be the key difference between physical and cognitive measurements.
That's fascinating.
Yeah.
Okay, so let's dive into each of these concepts a little bit deeper.
Yeah.
So first, projective measurements. We've talked about those a bit. They're defined by these projection-valued measures. And essentially, when you make a measurement and you get a result, the system's state collapses into the state that corresponds to that result. And as we've seen, the paper argues that these are really fundamental, but maybe not enough to explain all these cognitive phenomena.
Exactly.
So then we have these sharp, repeatable, non-projective measurements.
Yeah, the SRPs. So what makes them special?
So these are really interesting because they still have this property of sharpness, meaning they give you like a definite outcome, like a yes or a no in a decision.
Right.
And they're also repeatable. So if you measure the same thing again right away,
you're going to get the same answer.
Okay.
But the key difference is that their state update is not projective.
Okay.
So the system doesn't just collapse onto a simple state related to what you measured.
Right.
It can be more complex than that.
Okay.
And the paper suggests that this non-projective nature might be crucial for understanding more complex cognitive functions, especially memory.
Okay. Yeah, that makes sense.
Yeah.
Because, you know, if our memories just got completely overwritten every time we encounter new information, that wouldn't be very useful.
Exactly.
So we need something a little bit more nuanced, right? And then we come back to this distinction between observable non-commutativity and state update non-commutativity. So observable non-commutativity we talked about, that's like the position and momentum example. You can't measure both perfectly at the same time.
Right.
And early quantum-like models often attributed the question order effect, you know, where the order of questions influences the answers. They attributed that to observable non-commutativity, suggesting that like the questions themselves were incompatible in some way.
Yeah, like they were fundamentally clashing in our minds.
Right. But the SRP approach offers this other possibility.
Yes, state update non-commutativity, or what some people call non-commutativity.
Okay.
And this is all about whether the order in which you apply these state update processes matters.
Okay.
So even if the underlying observables, like the questions themselves in a cognitive context, are compatible, meaning their operators commute, you can still see a question order effect if the way your mental state is updated by each question doesn't commute.
Okay, so it's not necessarily that the concepts themselves are clashing. It's that the process of considering them in a certain order can change your state.
Yeah, and the Ozawa-Krennikov model that the paper mentions, it actually shows a question order effect even with compatible questions.
Wow.
Precisely because of this non-commutativity.
So it's like the journey matters more than the destination.
Yeah, it's like the process of getting to an answer can really shape what that answer ends up being.
And I think that's a really important insight for people to have just in their own lives.
Oh, absolutely.
Because it means that, you know, the way you approach a problem, the order in which you consider different pieces of information, that can actually change your ultimate conclusion. And then there's this response replicability effect, or RRE, which is basically this tendency to give the same answer to a question if it's asked again soon after.
Right. And the paper points out that if you try to model both the question order effect and the response replicability effect together, it's really hard to do that with just projective measurements.
Right.
Because the way a projective measurement works with this immediate state collapse, it's like you're wiping the slate clean every time.
Right.
So it's hard to maintain this memory of a previous answer.
That makes sense. Okay, so then they talk about this thing called QQ equality.
Yes.
Which I think is a really interesting concept.
Yeah.
So it's basically this mathematical relationship that holds true for projective measurements.
Yeah.
And it's been observed in a lot of data from social opinion polls.
Yeah, like the work by Wang and Busemeyer that the paper mentions.
Right. So it's like this consistency check for whether our minds are operating according to these projective measurement principles. But then more recent research in the field of aesthetics, you know, like how we judge art and beauty, they've actually found violations of this QQ equality.
It's like our minds are doing something different.
Right. It's like maybe appreciating art involves a different kind of mental process than answering a simple opinion poll.
Exactly. And what's cool is that SRP measurements, they have the flexibility to both satisfy and violate QQ equality.
Yeah, that's interesting.
So they're much more versatile.
Right. Okay. And then finally, they talk about invasiveness, which is basically when a measurement can potentially violate the formula of total probability, or FTP, which is like, you know, a cornerstone of classical probability theory.
Yeah, it says the probability of something happening can be found by adding up the probabilities of it happening under all the possible conditions.
Right. So if you violate that, that's pretty wild.
Yeah, it suggests that something non-classical is going on.
Right. And this is linked to things like non-Bayesian belief updates and the disjunction effect.
Yeah, which is where people's preferences can seem inconsistent depending on how the options are presented.
Right. So quantum measurements in general are invasive. And the paper points out that SRP measurements are also invasive, which could explain why sometimes we see these interference-like effects in cognition.
Yeah, it's like when you consider one possibility. It can influence how you judge another possibility.
Right, and that's not how classical probability should work.
Exactly.
Okay, so to summarize, why are these SRP measurements so potentially well-suited for understanding advanced cognition?
So the authors argue that their sharpness aligns with the fact that a lot of our conscious decisions are like these definite yes-no choices.
Right.
Their repeatability makes sense. If you think about how short-term memory works, like we hold on to recent thoughts, the non-projective aspect could explain how our memory can remain relatively stable, even as we're considering other information.
Right.
And then their invasiveness might be the key to understanding these situations where our judgments don't seem to follow classical probability.
Right. Okay. So they also briefly touch on this idea of state dependence. Can you explain that a little bit?
Yeah, so they point out that things like non-commutativity and even what we consider to be classical can actually depend on the state of the system.
Okay.
So in this case, that would be the mental state of the individual.
Right.
And this is really important in cognitive modeling. Because unlike in a physics experiment, we can't perfectly control or even know someone's mental state.
Yeah, that's true. It's a lot messier.
Yeah. Exactly.
Okay, so let's move on to our novel notions segment, where we like to take these ideas from the paper and think about where they could lead in the future.
Yeah, I love this part.
So given this paper's focus on SRP measurements and their potential for understanding cognition, what are some exciting new avenues for research that this could open up?
So one really fascinating possibility is to look for the neurophysiological correlates of these SRP measurements.
Interesting.
So the idea is if the brain is actually using something like SRP measurements for these complex cognitive tasks, could we actually see that in the brain?
Right. Like, are there specific patterns of brain activity or even like certain brain regions that become more active when people are doing tasks that exhibit these combined question order and response replicability effects.
Exactly. So imagine designing an experiment where people are answering these sequences of related questions.
Yeah.
And while they're doing that, we're monitoring their brain activity.
Right, like with fMRI or EEG.
Exactly. And we could look for these distinct neural signatures that show up when someone's replicability is high.
Right.
Even when the order of the questions is changing.
That would be amazing.
Yeah. And the impact of this research could be huge.
Yeah.
It could help us understand the actual neural mechanisms behind these quantum-like cognitive phenomena.
And that could lead to better models of decision-making, memory, maybe even consciousness.
Absolutely. It's a really exciting direction.
So what's another novel notion that you're thinking about?
So another really intriguing idea is to try to develop AI agents that are based on these SRP principles.
Interesting, because right now, AI models often struggle with things like maintaining consistent beliefs and being sensitive to context. And so could the math of SRP measurements offer a new way to build AI that's more robust and human-like?
Yeah, so imagine building a reinforcement learning agent where its internal belief state is updated using these non-projective quantum instruments.
Okay.
And then we could test its ability to handle tasks where the order of information matters.
Right.
And where a kind of response consistency,
like the RRE in humans, would be beneficial.
Yeah, so imagine like an AI assistant that learns your preferences, not just from what you ask for, but from the flow of your interactions.
Like the sequence of your requests.
Exactly. Or think about an AI recommendation system.
Yeah.
That doesn't treat each query as a separate thing.
Right.
But it builds up this nuanced understanding of your preferences.
Based on the order of your interactions.
Exactly. And this could lead to AI systems that are much better at reasoning under uncertainty, staying aware of context, and behaving more consistently over time.
So like in personalized education, for example, the AI could adapt its teaching style based on the student's questions and answers.
Exactly. Or in complex problem solving, where you need to maintain a consistent understanding across multiple steps.
These are really fascinating possibilities.
Yes.
I mean, it's incredible to think that by looking at this relatively unexplored area of quantum measurement theory, we could unlock new ways to understand both our own minds and how to build more intelligent machines.
Really exciting.
It is. It is so important to remember, though, that these are just speculative ideas.
Yeah.
We're just exploring possibilities here.
Of course, these aren't predictions of future research.
Right.
But they're definitely food for thought.
Absolutely. And on that note, we'll wrap up this deep dive.
Okay.
As always, the link to the paper is in the show notes.
Yeah, to check it out.
For those of you who want to go even dipper.
Absolutely.
Thanks for joining us.
Thanks, everyone.